The words hyperemia and congestion are often used interchangeably in medicine and pathology. And probably if you Googled acute passive hyperemia of the liver, it would probably have about as many hits as acute passive congestion. And so probably rightfully so, they're often used interchangeably. However, let's try to introduce them as two slightly different concepts. Hyperemia is exactly what it is. It's increased flow. So you think of hyperemia as being increased flow from the arterial end and a extension of that hydrostatic pressure, and flow a little bit further than it would normally go in the capillaries. Whereas congestion is thought of as being more of a passive process, and congestion is classically the result of increased venous hydrostatic pressure. So we talk about congestion in the liver or the lungs. Even though the word hyperemia is used, we're really talking about more correctly congestion rather than hyperemia. And that's what we've said right here. We said hyperemia is an active process and congestion is a passive process. And I would like to add that if the passive process is chronic, and by that I mean goes on for a long period of time, it's more likely to produce damage in that organ. For example, in the lungs, chronic congestion will result in increase in red cell breakdown and hemosiderin macrophages, or what we call heart failure cells. In the liver, chronic congestion can actually result in a necrosis of the liver, especially the central portion of the lobule, and elevation of enzymes, even cirrhosis if it's long-standing enough. So let's take some look at congestion of the lung, liver, and the brain. Well, here is congestion in the lung. The only thing you could really tell from the alveolar level, and I think even if you weren't an expert on pulmonary histology, you could see that these alveolar septae here are very, very, very red because every single one of the septal capillaries is congested. If that is allowed to progress or gets worse, there is then leakage of fluid as a transudate into the alveoli, like you see here on the right, and that's called acute pulmonary edema. If this process lasted long enough, chronic, let's say, there would be breakdown of these red cells and increase in hemosiderin, which would be rapidly gobbled up by the alveolar macrophages. This is what acute pulmonary edema looks like to the radiologist. First of all, there's a general infiltrate. That you can tell. This is basically filling up of the alveoli with fluid. And also, remember, it's a little bit worse in the more gravitational parts of the lung, isn't it? The lower lobes. In addition, they have these little lines called curly B lines, which is sometimes which enables you to see little segmental septae between segments of the lung. And they talk about air bronchogram, and perhaps we can theorize that if there's a lot of fluid surrounding a larger bronchus, like maybe here and here, remember I'm no radiology jock, you will notice a prominence of that air bronchogram in contrast to the normally airy stuff that's around it that is called lung is now water. So the air in the bronchial spaces are enhanced. In addition, something that you don't see here too well are effusions, or what they call blunting of the costophrenic angles. In my opinion, these are still both pretty sharp. So let's look at a air bronchogram, which is, I hope you can see that it's outlined. You can see the air in the trachea and in the right and left bronchi. It's a little more prominent than usual because the lung surrounding it is filled with water. And here's general infiltrate. And you see that little line there? Well, that is not a major fissure. That is a little separation between segments in the lung. And that is what they call curly B. It's not like Curly, one of the Three Stooges. It's called Curly, K-E-R-L-E-Y. Here's lungs that have been congested for a long time. And rather than having fluid in the alveoli, and maybe a little bit of blood, the blood is now broken down. So the macrophages come in and chew it up. And if you did a Prussian blue stain on these cells, you would see they would be as green or blue as hell, simply because the macrophages are chewing up the hemosiderin. And Prussian blue is a fairly specific stain for hemosiderin. Here we go. Here's our stain. And we could see that the macrophages are very blue. And when you see golden pigment that stains blue, you don't have to ask yourself whether it was melanin or bile or lipofuscin or hemosiderin. You know it's hemosiderin. Take a look at this, because this is something you probably ignored when you were cutting through your livers in anatomy. Do you see every one of these little red dots? Every one of these little specific red dots, especially here in the area where they're not confluent like they are here, that's a central vein. So what are you doing? You're looking at a liver with your bare eyes without a microscope, and you're seeing central veins. The reason you could see them is because they're congested. The reason why they're congested is there probably was a right heart failure. And here we go, microscopically, acute passive congestion. Do the central veins, like here and here, look congested? Yes, they do. Now, let's say that that process was long-standing enough. We now have necrosis surrounding the central vein, or what they call central lobular necrosis. And this is a chronic congested liver now. It's also called nutmeg liver, because if you cut the surface of a nutmeg, you can see it looks exactly the same. Now those are pinpoint red areas from acute bloody congestion are now brown because of the necrosis secondary to chronic long-standing central vein congestion. Now here's an organ that's congested, and it doesn't look swollen to me, for the simple reason is the brain cannot swell. It lives in a little steel cage which prevents it from swelling. However, can I convince you that the gyri are flat? And they're flat because they're being pushed against a bony structure. And for that reason, secondarily, the sulci are less accentuated. Now, even though the brain cannot expand, theoretically, if you remember, there is a basal cistern which could allow technically that space for expansion of the cerebellar tonsils. Or if you look at the uncinate process or of the hippocampus, you'll see there's technically a little area where it could push through the cingulate gyrus, can actually push through the tentorium a little bit. Or if you remember that falx is a big, hard, fibrous, membranous structure separating the two hemispheres and pretty much poking all the way down to the corpus callosum, but not exactly. So if there's a unilateral brain edema, you're going to have a little herniation through these areas. These are the three areas which you look at in every autopsy for cerebral edema. And do we want to go on? Sure we do, but let's, as long as we've got a couple seconds, let's introduce the next topic. Let's define hemorrhage very easily. Hemorrhage is blood that has escaped from its blood vessel boundaries. And we'll start that in the next 10-minute clip, and I thank you very much.